Okay, so in this video today, we want to look at the concept of the derivative, and the process of obtaining a derivative is called differentiation. So we're now launching into our topic of calculus, beginning by the concept of derivative and the process of differentiation. We'll look at applications of differentiation, and then we'll also be looking at integration as part of calculus as well. So our initial focus here is on the idea of derivative. What is derivative? How do we go about calculating derivative? So the key thing is that what we're trying to do with a derivative is find an equation that describes the gradient of a curve. So the key idea is that a curve doesn't have constant gradient. So a straight line has a gradient of 2 or 3 or -7 or whatever it might be. And that means at every single point on that line, the gradient is 2 or 7 or whatever it might be. Okay? When we have a curve, the definition of a curve is that the gradient is not constant. The gradient is constantly changing. Okay? A curve might initially start off with a negative gradient, then it might have a 0 gradient, and then it might have a positive gradient. It might be small initially, and then it might get steeper. Okay, so the whole idea is that gradient is changing constantly with the curve. So we're not going to be able to calculate a numeric value for the gradient for the entire curve. We want to be able to get an equation that describes the gradient at any point on the curve. And then we can calculate the gradient at a particular point by substituting a value into that equation. So we want to be able to think about this idea of gradient of a curve. So I've got this diagram here, and I'm going to in a minute flick across to a more interactive version of this diagram that we can talk further about. So what we want to look at here is we want to start by focusing on what we're trying to ultimately do is find the gradient of the green curve at the point M. Okay, so the key idea about gradient is that the gradient of a curve at a point is equal to the gradient of the tangent to the curve at that point. So definitionally, a tangent is a straight line that has the same gradient as the curve at the point where they meet. Okay, so the gradient at this point M, the gradient of the green curve is equal to the gradient of the red line. Okay, those two things are equal. So we're going to do that by calculating the gradient of a different straight line and then working out how we can get that to tell us about the gradient of the red line. And that what we're interested in here is going to be this straight line from M to N, which is called a secant. So a secant being a straight line that joins 2 points on a curve. You might also be familiar with the word chord. That's where we have a straight line that joins 2 points on a circle. More generally, joining 2 points on a curve, what we create there is a secant. Okay, so we want to think about the gradient of this secant. Now let's talk about a couple of things first. So the key thing here is the point M has an x-coordinate of x. Now you could call that anything, and in the diagram I'm going to flip to, it's going to be called A, but the process is still the same. Okay, so let's say the x-coordinate of that point is x, then that means the y-coordinate of the point M is f of x, substituting x into our function, which is f. Okay, so M has coordinates x, f of x, and then we're going to have another point which is just going to be h units horizontally away from M. Okay, so if this is going to be h here, that makes this x coordinate x plus h, and therefore the coordinates of the point N become x plus h and f of x plus h. So substituting the x value into the function. Okay, so we now have these 2 points, M and N, and a secant joining them. So what we, as I said before, what we want to do is be able to consider the gradient of the secant and then use that to help us calculate the gradient of the tangent at M, and hence the gradient of the curve at M. So we've already talked about the fact that obviously this horizontal distance, a gradient, is rise over run. We need to think about horizontal change and vertical change. So the horizontal change there is h. X plus h minus x is h. Okay, and the vertical change here is going to be f of x plus h minus f of x. Okay, so therefore, and I think there's a space for us to write this further down in the notes, these dot points just go through what's happening in this diagram. So let M be a point on the curve with coordinates x, f of x. A tangent is drawn at M, and it should be recalled that a tangent is a line with the same gradient as the curve at the point where they intersect, so at the point M. Let n be a point on the curve with coordinates x plus h, f of x plus h, and this is where h is small. So we've got to imagine here we've really zoomed in close to these points on this graph. So we're looking at a very enlarged version of something, and those points m and n are actually very, very close together because h is a very, very small value. A secant, a straight line joining 2 points on a curve, is drawn joining m and n. Great, we've talked about that. And the gradient of the secant gives the average gradient of the curve from x to x plus h. So we want to write down an expression for the gradient of the secant mn. Okay, and we've talked about that that's rise over run. So our rise being f of x plus h minus f of x, and our run being h. Okay, and so therefore the gradient of the secant is going to be f of x plus h minus f of x, which is the rise, the vertical change between those 2 points, over h, which is the run, the horizontal change between those 2 points. Okay, I'm going to pause for a minute now and just go across now to the interactive version of this diagram so we can see visually what we're talking about here in terms of how are we going to use that blue line to approximate or to allow us to calculate, in fact, the gradient of the red line. So I'm just going to pause this here for a minute and jump over there, and then I'll come back here and resume talking through the notes. Okay, so here we've got a similar diagram as to the one you can see in your notes that we've just talked through. Some of the letters here are different, and unfortunately the colours have switched different locations here. So we now have our curve f of x defined by a red line. We have our 2 points that here are called P and Q, where they were M and N in your notes. And also I'm calling the x coordinate of P A here rather than x. But essentially it's still exactly the same idea. So therefore the coordinates of P are A, f of A, and then Q is another point that is just a small distance h away, a small horizontal distance h away. So its x coordinate is A plus h, and therefore its y coordinate is f of A plus h. We've got on the x-axis here the difference between those two x coordinates, the run, if you want to think about that, in terms of gradient being rise over run, so the horizontal change between those 2 points, a plus h minus a, so that is h, okay? And then the vertical distance between those 2 points, so the rise, when we're thinking about gradient, is f of a plus h minus f of a. We've got those drawn here. So we should be able to see, as I move the point Q, how those distances, the vertical distance and the horizontal distance change. What we're also seeing here is, so remember what we're trying to do is use our blue secant, so the line from P to Q, use the gradient of that line to allow us to calculate the gradient of the green line, which is the tangent to the curve at the point P. Remembering that the gradient of the tangent to the curve at the point P is by definition the same as the gradient of the curve at the point P. So what I've got the program here calculating is it's currently calculating the gradient of, now that should say secant rather than chord, but it's calculating the gradient of the secant from P to Q, so the blue line, and it's also calculated the gradient of the tangent at P, okay, which is what we're trying to calculate. So we're trying to use the blue gradient to calculate this gradient, which should be 1.41. So the whole idea is, the way we're going to be able to use the blue line to approximate the green line is to continue to move Q closer and closer to P, so that what we see happening, and you can see that in the numbers changing at the top, is that the closer and closer and closer Q gets to P, the better and better and better, or the closer and closer and closer its gradient comes to being equal to the gradient of the tangent at that point. Okay. So what we want to essentially do is think about moving Q closer to P along the curve. And we're going to be able to do that by making h, the horizontal distance, small. So as Q moves closer to P, h becomes closer and less and less and less. H approaches 0. So the gradient of the green line is equal to the gradient of the blue line as we make h small. So it's the limiting value of the gradient of the blue line as h approaches 0. And that's the whole idea about how we calculate gradient of a curve at a point. So I'm going to go back over to the notes and talk through the rest of the theory there, and then work through those examples. Okay, so here we are back here, and we saw the whole idea about using the blue line to approximate the gradient for the red line, or to allow us to calculate the gradient for the red line, is about making this distance h smaller and smaller and smaller. So we want to move the point n along the line, which will therefore make the value of h smaller, therefore make the blue line more and more like the red line, and hence we're getting a better and better and better version of the gradient of the line, the red line. So as it says here, our purpose now is to find, once we've got the expression for the gradient of the secant, the blue line, our purpose now is to find the gradient of the tangent at m by using the secant mn. And we will do this by making h small. That is, by considering the limiting value of the gradient of the secant as h approaches 0. This will mean that x plus h will move towards x, n will move along the curve towards m, and the gradient of the secant mn will approach the gradient of the tangent at m, and hence the gradient of the function or the curve at m. Okay, so essentially this is what's going to happen. So what we're going to be doing here is we essentially want to look at, okay, if we actually want to have the gradient of the curve, what we're going to be doing is taking this gradient of the secant and looking at what happens to that as h approaches 0. So we're looking at the limiting value as h approaches 0, and that's going to give us the gradient of the curve. Okay. Alright, so that's where we get this rule over here. Apologies about the keyboard. Okay, so that's where we're going to get this rule over here. And this rule is going to give us an equation that describes the gradient of a curve at any point on that curve. So any x value on the curve, this will give us the equation that describes the gradient. So the rule created using this process is called the derivative, or the gradient function of f. And one notation, I'll talk about notation in a minute, but one notation we use if we're looking at the derivative of f is f dash x. Okay. So the derivative of f of x is f dash x, and it's equal to the limit as h approaches 0 of f of x plus h minus f of x, that's the rise of the secant, divided by h, which is the run of the secant. And as we look at what happens as h becomes small, the secant is getting smaller and smaller and smaller, and its gradient is approaching the gradient of the tangent. Using this rule is called differentiating by first principles, and you do need to understand and be able to use this rule. Okay, we're going to look at over the rest of this topic about how we can establish more efficient rules for all the functions we're going to work with commonly, but they all come back to this derivative by first principles, and in fact I'm going to show you how all those rules derive from this first principles process before we then actually go ahead and use them. So what we want to do today is actually practice how we're going to use this rule, and I do want to reinforce that you do actually need to know how to do this. You can't just go, oh, I'm just going to forget that and worry about, I already know how to differentiate this without needing this ridiculous rule. So it is something you need to have an understanding of. Okay, so this example here, we're going to use differentiation by first principles to find the derivative of f of x, where f of x is x squared plus 2x plus 5. Now, many of you might recall your rules for differentiating from last year, and you might already be shouting at me, oh, it's just going to be 2x plus 2. And yes, it is going to be 2x plus 2, but let's make sure that we can get to that point by using this process of differentiating from first principles. Okay, so f of x is x squared plus 2x plus 5. So we're going to be able to put that straight away in here where there's f of x, being careful that we'll be subtracting all of that. We're also going to need to calculate f of x plus h. So let's do that first before we then go to our actual derivative by first principles. Just get some of this algebra out of the way off on the side. So f of x plus h means everywhere there is an x in f, we're going to now replace it with an x plus h. Okay, so we have x plus h all squared plus 2 times x plus h plus 5. Okay, so I'm going to expand all that out, tidy it up, collect some like terms before we then go into our rule for the derivative. Okay, so x squared plus 2hx, or 2xh, doesn't matter, plus h squared. Here we've got 2x plus 2h, and then we've got plus 5. Okay, we don't really have any, there are obviously x terms, we could combine some things together, but I'm just going to leave it at that for now. So let's now go to our derivative. So we know that the derivative f dash x is equal to the limit as h approaches 0 of, sometimes it's good to write brackets around what you're taking the limit of, and it's really important that until you've actually taken the limit, you continue to write that limit. I see a lot of problems with notation in these questions. Equally, when you write f dash x, please make sure that the thing you write on the other side of the equal sign is actually the derivative. So without the limit of it as h approaches 0, it doesn't equal the derivative, okay? And obviously there'll be other examples of where I'll repeat that throughout this topic. So we're taking the derivative is equal to the limit as h approaches 0 of f of x plus h, which is this big ugly algebraic expression I've just calculated above. So we'll write this in here, 2hx plus h squared plus 2x plus 2h plus 5. And then we need to take away f of x. And obviously we need to be careful that we're subtracting all of f of x. So it's minus all of x squared plus 2x plus 5. And that's f of x plus h minus f of x. And we are now all over h. Okay, let's tidy up the numerator a little bit. So we're not taking the limit yet, so this is still going to be equal to the limit as h approaches 0. Now on the numerator we see we've got some like terms which are now cancelling out. We've got x squared minus x squared. We've got 2x minus 2x, and we've also got 5 minus 5. Okay, and so all we're left with on the numerator is 2hx plus h squared and plus 2h. All divided by h. Now the simplest way to calculate a limit, and we do a little bit of talking about limits in year 11, I'm not going to talk too precisely about them here because we only really need to be able to take a limit as h approaches 0 for this purpose and this purpose only. Now if we want to think about what happens as h approaches 0, essentially the quickest way to do that is to substitute h equals 0 into the expression. Now the reason I haven't done that already is because we've got this problem happening down here. Okay, if I were to make h equal to 0 right now, I'm dividing by 0 and we've got something that's undefined or certainly indeterminate. So we need to first manipulate the expression to a point where then we will be able to substitute in h equals 0. And until you can sub in h equals 0, your equation is still equal to the limit as h approaches 0 of something. Okay, so now let's divide each of those terms by h, because h is a nice common factor in this fraction. So 2hx divided by h is 2x, plus h squared divided by h is h, plus 2h divided by h is 2. Okay, so now if we were to think about, alright, when h approaches 0, so as h approaches 0, this term here is essentially going to disappear. Alright, and we're going to be left with, now once we've taken the limit as h approaches 0, we're just going to be left with 2x plus 2, which was the prediction I made earlier for those of you who remember how to differentiate this process using a rule. And obviously differentiating by first principles is what's going on in the background of using that rule, and we need to be able to show that we can do that ourselves. Okay, part B says hence, so that means use what you found in part A. So we're going to use our derivative or our gradient function to find the gradient of the curve when x equals negative 6. Okay, so we've now got an equation that describes the gradient. That's what this 2x plus 2 is. That will give us the gradient of the curve f of x. So if we want the gradient of the curve f of x when x is equal to negative 6, we want to work out the derivative, the gradient function, when x is negative 6. And so that is going to be 2 times negative 6 plus 2, which is negative 12 plus 2, which is negative 10. So the gradient of this particular curve, this parabola, x squared plus 2x plus 5, at x equals negative 6 is negative 10. Okay, part 2 of part B is to find the coordinates of the point on the curve where the gradient is 10. Okay, so again, f dash x is describing the gradient at any x value. So if we want to know where the gradient is 10, we want to know where f dash x is equal to 10. So that is where our derivative for this particular curve, 2x plus 2, is equal to 10. And that will happen when 2x equals 8, and therefore when x equals 4. Now we want the coordinates of the point. So we've now found the x coordinate of the point, where the gradient is 10. and so we need to find the y coordinate. Now sometimes I find students find this complicated and they're really tempted to take this x value and sub it back into their derivative. But if you do that, you're going to find you get 10, because the derivative isn't telling you about the y coordinate of the point, the derivative is telling you about the gradient. So we already know when x equals 4 the gradient is 10. We don't want to put that back into there, that will just tell us something we already know. We want to work out the y value. We want to go back to our original function, x squared plus 2x plus 5. Okay, so that means that we know that f of 4 is going to be 4 squared plus 2 times 4 plus 5, so going back in, 5, going back into our original function, so that is 16 plus 8 plus 5, and so 29, and so therefore the gradient is 10 at the point with coordinates 4, 29. Okay, the next thing I want to talk about, so derivative by first principles is a process you're going to need to be able to do. There'll be an opportunity to practice that in the exercise I'm going to set. Once you've got your derivative function, having an understanding of how that connects to gradient. It allows you to find the gradient of a curve at a particular x value, or it enables you to find which x value will give a particular gradient. Okay, let's talk a bit more about the notation. So far we've met f dash x as being the derivative of f of x. And that's when we've got our original equation given in function notation. So here, repeated in the first line of this table here, f of x, the derivative of that is f dash x. Okay. The derivative of the function g of y would be g dash y. The derivative of the function h of t would be denoted h dash t. It's really, really important that your notation matches the original definition of the function. Okay. If your function is not called f of x, its derivative is not f dash x. Okay, so commonly we might not be given the function in function notation. It might just be y in terms of x. For example, we might have been given that equation in the previous example as y equals x squared plus 2x plus 5. And in that case, the derivative would not be called f dash x. Okay, so we need a different notation called Leibniz notation. Okay, and that is where we write this slightly ugly fraction, and many people like to try to avoid that, but actually it's not avoidable. If you're calculating the derivative of y with respect to x, so you're differentiating a function that is y in terms of x, and you're differentiating that function, therefore you're finding the derivative of y with respect to x is the phrase we would use. And then we write that as dy dx. This notation essentially evolves out of the fact that gradient is small change in y over small change in x. And this Greek letter delta is used to represent small change. So the gradient of the curve is about looking at the small change in y over the small change in x, okay, rise over run, to get the change in the grade, so to get the gradient. Okay, so that's where that dy dx comes from. Okay, that's capital delta. Lowercase delta looks very much like a d, and eventually that's evolved into dy dx rather than delta y delta over delta x. Okay, so dy dx, change in y over change in x, gradient. Okay, if your equation is x in terms of t, so let's say we've got, x equals 5t plus 5t squared minus 7t, then if we drew that graph, this is a t-axis and this is an x-axis, and so the gradient isn't change in y over change in x, it is change in x over change in t, rise over run. Okay, so that would become dx dt, derivative of x with respect to t. If we have an equation that is a in terms of r, let's do a common one, a equals pi r squared, then its derivative will be change in a over change in r, derivative of a with respect to r. Okay, so dA dr. Alright, then we've got a third notation that's also really important. If you don't have an equation or a function, you're simply being asked to differentiate an expression, then it's not going to be equal to f dash x or dy dx. Okay, so we want to be able to have a notation that allows us to talk about derivative as an operation. Okay, and so if we have an expression in terms of x that is to be differentiated, we use this operator d dx. Okay, and then a bracket. So essentially I'm talking about the sort of question that might say, find the derivative of that. Okay, it doesn't equal y, so it's not dy dx. It doesn't equal f of x, it's not f dash x. We just want to define the derivative of that. And so we want to differentiate with respect to x that. Actually, the way this is really written is essentially we're finding the derivative of x cubed minus 4x with respect to x. But just to avoid such a big cumbersome fraction, we tend to take that little bracket and write it off the side of the fraction. But it is the same thing. So it says that on the next line here. So we can either write this as derivative with respect to x of square root of x cubed minus 4x, or we can write it as the derivative of the square root of x cubed minus 4x with respect to x. Okay, so being able to transition between these three notations is really important. You can't just decide I'm only going to write this every time. You need to be able to respond to the question and the way the question's phrased and the function as it's defined in the question. Okay. Alright, so let's have a look at another example here. So if y equals 3x minus x squared, find dy dx using first principles. Okay, so this time we're going to call it dy dx, but it's still the same rule. The derivative or the gradient function is found by taking the limit as h approaches 0 of the gradient of the secant, which is f of x plus h minus f of x, all divided by h. Okay, so that's our derivative. So we're going to do that for this particular function. All right, let's maybe we'll do the substitution at the same time in this case. So dy dx is going to be the limit as h approaches 0 of f of x plus h. So again, that's taking x plus h and substituting it wherever there is an x in the function. So that's going to be 3 times x plus h minus x plus h all squared, and then taking away f of x, which is 3x minus x squared. Okay, and then we've got all of that over h. Alright, let's expand out the numerator. Limit as h approaches 0. I haven't taken my limit yet, so my derivative is equal to the limit of this expression. Let's expand out the brackets. So we've got 3x plus 3h. Now x plus h all squared, remember, is x squared plus 2hx plus h squared. And so we're subtracting all of that. So we're going to have minus x squared minus 2hx minus h squared. And then again, we're subtracting f of x, so it's minus 3x and plus x squared. Okay, and we've got all of that over h. Alright, so we've got some things that are cancelling out on the numerator here. We've got negative x squared and plus x squared. We've got plus 3x and minus 3x. Alright, so then let's also think about dividing. Each of the terms remaining on the numerator has h in it, so h is a common factor, so let's divide each term by h. We still haven't taken the limit as h approaches 0. We're just simplifying this expression, this fraction in the bracket. Okay, so 3h divided by h is 3, negative 2hx divided by h is negative 2x, and negative h squared divided by h is negative h. Now that we've got rid of h in the denominator of the fraction, we can now take our limit as h approaches 0. What that's going to mean is this term here essentially becomes 0, and we're just going to be left with 3 minus 2x. So we've now calculated that dy dx, the derivative of y with respect to x, the gradient function of this for this particular equation, is 3 minus 2x. Okay, part B, we want to calculate the set of x values where dy dx is equal to 0. Okay, so we've got dy dx in the previous line, so that means we want to know where 3 minus 2x is equal to 0. So that means 2x equals 3 and x equals 3 on 2. Technically we were asked for a set, so I'm going to answer as asked, so therefore x is an element of the set that contains just the one number, 3 on 2. Find the set of x values where dy dx, the derivative or the gradient, is bigger than 0. So where is the gradient positive? So this is going to be where is 3 minus 2x bigger than 0. So 3 bigger than 2x, 3 on 2 bigger than x. So that is where x is less than 3 on 2. So again, thinking about a set, x is an element of the interval from negative infinity up to 3 on 2, not including 3 on 2. If you want to write that as an inequality, you would need to say we're going to have the set of x values such that x is less than 3 on 2. Okay. So again, revisiting some of that set notation, this question technically asks us for a set of x values. So let's make sure that we give it as a set. And so part D here, we want to calculate the set of x values where the derivative is less than 0. So that is where 3 minus 2x is less than 0, where 3 is less than 2x, where 3 on 2 is less than x. Okay, so that is x is bigger than 3 on 2. And so that means x is an element of 3 on 2 to infinity, or we could write that as the set of x values such that x is bigger than 3 on 2. Okay, so we're thinking about here where the gradient equals 0. So the gradient equals 0 at 3 on 2. So our original function here is a quadratic. So the point where the gradient equals 0, that will be the turning point. So the turning point is happening at 3 on 2. Where is the gradient positive? Where is the gradient bigger than 0? That happens when x is less than 3 on 2. And that's because this is a sad parabola. Okay, so you've got your turning point at 3 on 2. You've got positive gradient when x is less than 3 on 2, graph is going up, and you've got negative gradient, graph is going down, when x is bigger than 3 on 2. Okay, the last thing I want to talk about in this first video is this strictly increasing and decreasing functions. Now this is a really peculiar thing that VCAA made a clarification about via a bulletin a number of years ago now. And they made this distinction between when a function is increasing versus when it is strictly increasing. And it's actually a slightly controversial definition. So for those not sitting the VCE and watching this video, I want you to take this with a pinch of salt and say that a number of people don't agree with this definition. But our examining body has decreed that this is what they mean when they refer to something being strictly increasing or strictly decreasing. So obviously an increasing function, or if we want to think about where a function is increasing, it's going to be where it has positive gradient. Okay? And if we want to think about where a function is decreasing, it's going to be where it has negative gradient. But if we want to talk about the set of values over which a function is strictly increasing, we sort of have a definition that's less to do with gradient and more to do with points on the right having to be higher up than points on the left. Okay, so let's say, for example, so what I mean by that is if we have, let me say, for example, draw a parabola here, okay, and actually let me make it a bit wider so I can be clear. So we agree that wherever there's positive gradient, the function is increasing. So let's say that this is, okay, so if this is, so if this is the point A, let's say that's A and let's say that's B, okay? So we know that at A, the gradient is 0. So normally we'd say the function isn't increasing at A, and that's a true statement. The function is not increasing at A, it's stationary at A. It's got 0 gradient. The rise over run is 0, the rate at which the function is changing is 0, okay? But the question isn't about, isn't actually asking you where is the function increasing. It's asking you to give a range of values between which the function is strictly increasing. And we've got this definition here, okay? So f of a, remember, didn't mean to erase. So f of a, remember, is the y value of this point if the x value is b, and f of b is the y value of that point, okay? So what it's saying here is the function is strictly increasing over a closed interval, a to b, including a and including b, if f of a is, I've got them around the wrong way, if f of a is smaller than f of b for all x values. So in this instance, if I pick a and b as being this value and this value, it would be true, it is true that f of a is smaller than f of b. That is, the point to the left is lower down than the point to the right. Okay, so it's certainly strictly increasing from a to b, including a and b. Okay, So if we were to include, and b could be any point up anywhere here. So let me make this a cubic perhaps so we can see a bit more clearly. So let's say I've got a cubic. Let me do it the other way. Let's say I've got a cubic that does this. Okay, so let's say that's the point A, f of A. That's clearly the point B, f of B. Okay, we've got positive gradient between A and B. So increasing function between A and B, not including A and not including B, because the gradient is 0 at A and B. However, it is a strictly increasing function where x is an element of A to B, including A and B. And the idea is that I should be able to pick any 2 points within this interval, that point and that point, this point at A and this point here, this point here and this point at B. And no matter which pair of points I choose, the one on the left will be lower down than the one on the right. F at A, f at the smaller x value will be lower down than f at B. So the value of the function at the bigger x value. Okay, so therefore this is going to be by this definition, this is a strictly increasing function from A to B, including A and including B. Essentially, for the strictly increasing questions, you can just think about it as being where has it got positive gradient and then include the endpoints if you want to avoid too much complication here. The opposite would be true for strictly decreasing, okay? So strictly decreasing, let's say we've got this cubic here, let's say this is the point A, f of A, this is the point B, f of B. If I pick any 2 values between x equals A and x equals B, including x equals A and B, the value of A will always be high. F of A will always be bigger than f of B. Okay, the point on the left will always be higher up than the point on the right, and therefore the function is going down over that interval. It is strictly increasing over that interval. Now, I want to be really clear about the fact that you might say, okay, but if I make B here, then it's also going down. F of A is smaller than f of B, f of B. But the point is that you should be able to choose any point within this interval. Okay, any 2 points within the interval, and f of A will always be bigger than f of B. So if I were to be talking about these 2 points here, that wouldn't be true, because I could pick this point here and this point here, and this smaller x value has a lower y value than this one. Okay, so from here to here, the function is not decreasing; it's increasing. So it needs to be the biggest set of values where you can pick any 2 points in that interval, including those endpoints, and if it's increasing, the point on the right will always be higher up than the point on the left. If it's decreasing, the point on the right will always be lower down than the point on the left. Okay, I don't want you to invest too much time worrying about this. Okay, this is not going to be a really big thing. And in fact, since they clarified this position and so many people argued that they didn't agree with it, they haven't really asked it very often, although in last year's exam they did. And I have been saying for a long time, don't worry about it. They made this definition. It's a bit controversial. They never ask it. And then last year they actually did. So I don't want to tell you to ignore it completely, but also it's not going to make up a big part of the course. So this particular function here, f is strictly increasing for x is an element of -2 to 3, including both of those points. And that's because I can pick any 2 points within this interval, and the one on the left will always be lower down than the one on the right, even if I choose 3 as one of my points or -2 as one of my points. Okay, it will still be true. -2 and this point here, the y value at -2 is lower than the y value at whatever that point is. I could pick, this point here and this point up here at 3. Okay, the y value at this point is lower down than the y value at 3, and so therefore between that range of values, the function is increasing. Okay, so let's have a look at one example here to finish off. So find the largest interval for which g of x equals x plus 1 times 4 minus x is strictly increasing. Okay, so we've got a quadratic function there with x-intercepts at -1 and 4, and it is a sad parabola. Okay, so -1, 1, 2, 3, 4. x-intercepts here and here. We have got a sad parabola, so halfway between we're going to have a turning point somewhere up here, and we're going to have a y-intercept. Let's calculate a few things. So g of 0 will be the y-intercept, so that's going to be 1 times 4, so the y-intercept is at 4. The turning point is going to happen at halfway between -1 and 4. Turning point at x equals halfway between two numbers. We can always find by averaging them, or you can probably see this one by eye having drawn the diagram. So that's going to be at 3 on 2, or 1.5. And so therefore the y value of that turning point, g of 3 on 2, is 3 on 2 plus 1 times 4 minus 3 on 2. So that is 3 on 2 plus 2 on 2, so 5 on 2, multiplied by 8 on 2 minus 3 on 2, 5 on 2. So we've got 25 on 4, okay, which is 6 1/4. Alright, so my y-intercept's at 4, so let's say we've sort of got, the y-intercept doesn't really matter to the answering of the strictly increasing, actually it's really just about the turning point. And in fact the y value of the turning point's a little irrelevant as well, but I've calculated that here for now. So it's really just about the x value of the turning point here. We want the largest value for which the function is strictly decreasing. So we want to think about negative gradient, which is happening on this side. So we clearly have negative gradient when x is bigger than 3 on 2. So we can clearly see that the derivative is, less than 0 when x is bigger than 3 on 2. But in terms of this definition of strictly increasing, we're going to be able to include 3 on 2 in the range of values for which the function is strictly decreasing, because we could pick any 2 points within that range and the point on the left would always be higher up than the point on the right. Okay, so we're going to say we are strictly decreasing for x is an element of 3 on 2, including 3 on 2, up to infinity. Obviously strictly increasing from -infinity to 3 on 2, including 3 on 2. So 3 on 2 would be included in both the range of values for which the function is strictly increasing and the range of values for which the function is strictly decreasing. So essentially think about strictly decreasing, where is the gradient negative, and then you can include the endpoint in the range of values for which the function will be strictly decreasing. As I said, I don't want you to spend an inordinate amount of time on that. In this particular section, I want you to focus on the derivative by first principles, being able to execute that, so substitute into that and use that rule to find a gradient function, and then having a sense of how to use the gradient function, finding gradient at a point, or finding when the gradient is equal to a particular value, or where the gradient is equal to a particular value. And also being precise about your notation. Is it f dash x? Is it dy dx? Is it dx dA? Is it g dash t? Is it what should my derivative be called? Okay, the work today is in a worksheet. In fact, much of the work through Chapter 9, I'm going to be setting worksheets rather than work from the textbook, and those worksheets are all included in the appendix of your blue book. So at the back of your blue book in Appendix A is a worksheet called the derivative. That's the work you should be doing today. Please do the work in your exercise book still. I haven't allowed space on the worksheets for working out, so simply refer to the worksheet as you would your textbook and complete the questions in your workbook.